Describe the graph of the following functions. Let's look at z equals x minus 2y. Z equals x minus 2y. We can rewrite this as x minus 2y minus z is equal to 0. And this is a plane in 3 dimensions in R3. It goes through the origin. If x and y are 0, then z is 0. So it goes through the origin. And it has normal vector 1, negative 2, negative 1. And we can visualize this plane. Let's see, 1, negative 2 rather, negative 1. There's our normal vector. And we can visualize this plane with the use of level curves. Level curves are drawn in the xy plane, and each level curve corresponds to a various height or level of the surface in question. So we pick a particular value for z, like maybe z equals 2, and then we substitute that in, and we get 2 equals x minus 2y, and this is a line in the xy plane. Let's see, what line is this? 2y is equal to x minus 2, so y is equal to 1/2 x minus 1. So something like this, well, maybe not so steep. Slope of a half. So this plane corresponds to the height z equals 2 of the surface, which is a plane. We'll draw a few more of these level curves. If z is 0, then we get 0 equals x minus 2y. And so y is equal to just x over 2. So that line is they're parallel lines. This is the line corresponding to z equals 0. If we let z equal 4, then we get x minus 2y is equal to 4, which is the line y equals x over 2 minus 2. And that one is parallel to this one again. Z equals 4. Z equals negative 2 would give us a line over here. Z equals 6 would give us a line here. So these lines help us to visualize the plane. So as we move along these lines in this direction, the plane is rising. The height of the plane goes from negative 2 on this line to 0 to 2 to 4 to 6. So this is acting like a topographical map. It's like this was a mountain or something, and this is the height of the mountain, and these are the points on the mountain that are at that height. Except we don't have a mountain, we just have a plane. So these are the points on the plane that are at the height 6. These are the points on the plane that are at the height 4. These are the points on the plane that are at the height 0, ground level, the same height as the xy plane. So this is the trace in the xy plane. Okay, let's look at the others. The next one we have is z equals x squared plus 4y squared. Z equals x squared plus 4y squared. This is an elliptical paraboloid. Which looks kind of something like this. If I draw an ellipse and then put the vertex, and we have some kind of parabolic surface, maybe kind of like an upside down umbrella. although it's elliptical in its cross sections, as we shall soon see. Let's look at the traces. If we let x equals 0, so the trace in the yz plane is z equals 4y squared, and that's a parabola. So we can see the parabolic effect there in the yz plane. And if we let y equal 0, then we get z equals x squared, which is also a parabola. And so we see that in the xz plane, we also have a parabolic cross-section. So that explains the paraboloid part of the description of the surface. The elliptical part comes from looking at the level curves. So for the level curves, we pick values of z. If z equals 0, then our surface would be, the points on our surface would satisfy the equation x squared plus 4y squared equals 0, and this is just the origin. So the only point that's at the height 0 is the origin. And if we take z to be negative, then the equation x squared plus 4y squared equals some negative number, negative 1 or something, then this equation has no solutions. So this paraboloid never goes below the xy plane. The height is never negative. Okay, so if we take a height at, say, 1, z equals 1, then the level curve is x squared plus 4y squared equals 1, and in the xy plane, this is an ellipse. It's an ellipse. If we take 1 here, if x is plus or minus 1 and y is 0, so that should be plus 1, and if y is a half or negative a half, so we get this ellipse here. So we get an ellipse that's a little bit elongated in the x direction. This one corresponds to z equals 1. If we take z equal to 4, then we have x squared plus 4y squared equals 4, and that would take the x out to 2. Let's make this one a different color. And the y and the x is a negative 2 over here, and the y would be 1 or minus 1. So it's kind of got the same eccentricity. It's distorted in the same fashion as the previous ellipse. It's just a little bit bigger. This one corresponds to z equals 4. And there was the origin. So this is like a top-down view of the elliptical paraboloid. So this is the lowest point. These points in blue are at the height 1. These points in red are at the height 4. And if I pick maybe x squared plus 4y squared equals 100, make it much bigger, then x would be plus or minus 10. So we would have a much bigger ellipse. This would be 10 over here and minus 10 over here on the x-axis. So that's a little bit not to scale. And then y would, if x is 0, y would be, y squared would be 25. So y would be 5 or negative 5. So the eccentricity is the same. It's got the same proportions. The minor axis is half of the major axis, and this is not how you draw an ellipse, but there you go. So these points have height z equals 100. So we can see the elliptical nature. The cross sections at various heights are ellipses, concentric ellipses. So that second one was an elliptical paraboloid. And the last one, the last surface was z equals the square root of x squared plus y squared. So this one is a right circular cone vertex at the origin. If x and y are both 0, then z is 0, and z is a positive square root, so z is bigger than or equal to 0 at all points for any xy. So this goes through the origin, and the traces, if we let x equals 0, the trace in the yz plane, it would be z equals the square root of y squared, which is the same as the absolute value of y. So z equals the absolute value of y, which if this is y and this is z, that looks like this. And that looks like a cone. The cone would have that absolute value feature together with, since it's a circular cone, it should have a circular feature as well, and we'll discover that when we look at the level curves. The other trace in the xz plane, y equals 0, so z equals the square root of x squared, which is the absolute value of x, so it's the same trace, just turned 90 degrees in the x-axis. Now for the level curves, pick various values for z. Again, if z is 0, then the only point corresponding to that is the origin, not exactly a curve, just a level point, if you will. And let's take z equals 1. That gives us 1 equals the square root of x squared plus y squared, and it would be helpful to square this and get 1 equals x squared plus y squared. That's the unit circle. So there's the circular part of our cone. So this corresponds to z equals 1. If z equals 4, 4 equals x squared plus y squared after squaring both sides. No, wait. If z equals 4, we get 4 equals the square root. And square both sides, we get 16 equals x squared plus y squared. So this is a circle centered at the origin with radius 4. So a bigger circle corresponding to z equal 4, a circle with radius 4. So we're looking, it's like a top-down view of the cone. At the center point here, the cone is at the height 0. On this circle, the height is at the point 1. At the height, the cone is at the height 1, and on this circle, the cone is at the height 4. And we'll just take one more. If we make z equal 10, then we get 10 equals the square root of x squared plus y squared, which is x squared plus y squared equals 100, a circle of radius 10. So a bigger circle, radius 10. So as we increase the value of z, the circles get bigger. Just what you would expect from a cone. As you go up, the circular cross sections will get larger and larger, and that's what we're seeing here in a top-down view. These are the level curves. Okay, so that's 3 surfaces. We had a plane, an elliptical paraboloid, and a right circular cone. Z is a function of x and y, x minus 2y for the plane, x squared plus 4y squared for the elliptical paraboloid, and the square root of x squared plus y squared for the right circular cone.